Welcome to E.P.G. Pachala. This is philosophy. The paper is logic, and the module for our presentation today is axiomatic system for sentential logic. The module is written by Dr. Smita Sirkar. I am Dr. Venusatini, Assistant Professor, Department of Philosophy, University of Hyderabad. We'll begin our lecture by trying to understand what is axiomatic system. Axiomatic method is used in deductive system, and by axiomatic method we mean we have a procedure, a technique by which we can identify all the truths in that domain. Now the truths vary in terms of their truth claim. Those which are so fundamental to the system, which are kind of self-evidence, are called axioms. And whatever we use these rules of inference to derive at certain truths are called theorems. So basically what we mean is we will have a set of self-evident truths or fundamental truths, and given these truths we are going to see how they are related to other truths which can be derived. They are called theorems. And for this derivation to be possible, we will have to employ some rules. Now we have two sets of rules. One, transformation rules. Two, rules of inference. Our derivation involving axiomatic method will somehow look like this. At the beginning we will have axioms, and these axioms will be transformed by a set of rules which are called transformation rules. We will also need some set of inference rules, so that using these rules we are able to derive some formulas which are called theorems. Basically what we are trying to do here is this, our attempt. We will first construct a suitable formal language for sentential logic. Two, we will identify a set of axioms, means fundamental truths for that system or domain. Three, we will introduce a set of rules called transformation rules and rules of inference. Number four, given these axioms and then the rules, we will try to derive some theorems. Now we will construct a formal language suitable for sentential logic. For any language to be possible, we will need syntax and semantics. But in this axiomatic method, we will not be concerned with semantics. However, we can have a set of alphabets and a set of grammar. So in our language, those will be called formation rules or rules of formation. We will identify a set of basic alphabets, and these are the alphabets. 1, P, Q, R, ... This P, Q, R stands for propositional variables, and we will have a pair of connectives, truth functional connectives, negation and implication. We will need a set of punctuation symbols, which are like round brackets, square brackets and curly brackets. Nothing can be a part of our alphabets except these three which are identified. So having provided the alphabets for the language, now we will look at the grammar, which is called rules for formation of sentences in our system. Every propositional variable will be a sentence in our system. That means P, Q, R. Now if we have a sentence which is symbolized here by alpha, then we can put a negation before a sentence alpha. That will also be a sentence. If we have a sentence alpha and another sentence beta, we can join these two sentences using a connective, which is conditional connective, and that will also be a sentence in our system. Now here is a closure principle. Nothing else is a sentence in our system unless generated by the application of these first three rules. Now that we have our basic symbols, which are alphabets, and also our formation rules, let us try to generate sentence. Q. Q is a valid sentence in our system because going by rule number 1, every propositional variable is a sentence. So it is a sentence. We can consider another one, negation R. By rule number 1, R being a propositional variable, it is a sentence. By rule number 2, when we negate any propositional variable, it becomes part of the sentence. Means it is a valid sentence. So negation R is a sentence in our system. Now let us look at the more complex system. Q implies not R. Is this a sentence in our system? Yes. By rule number 1, we see that Q is a sentence. We also see that R is a sentence because it's a propositional variable, and by rule number 2, negated R is a sentence. And by rule number 3, when we conjoin these sentences by implication, it becomes a sentence in our systems. We can also consider some sentences or what looks like sentences to us but which are not actually part of our language. The language that we are constructing can be termed as language P. Now, given alpha, is this a sentence in our system? We say it is not. Why? It is because alpha is not a propositional variable. Alpha rather is a meta variable which we are using from another language to stand for a formula here. What about P negation? Well, it is also not being formed in accordance to our rules. Rather, it has violated rule number 4, which says nothing else is a formula unless generated by the application of rule number 1, 2, 3, 4. So rule number 1, 2, 3 says nothing about P followed by negation. What about, let us take a look at another example, which is not a formula or a sentence in our system. Disjunction Q, negation R. This is not a sentence in our system because in our set of alphabets, first we don't have disjunction, and the sequence, that is the order in which the variables are placed, is not in accordance with the rules. So this is not a sentence in our systems. We can introduce new symbols with the help of the existing symbol. Now what we do now here is, in our set of symbols we only have implication. Now we want to use more truth functional connective in our systems. So how do we do this? We will use implication to define this symbol disjunction, so that we will also use disjunction for our proofs. How do we do that? Alpha implies beta is definitionally equivalent to not alpha or beta. So only this definition is allowed. That means only disjunction is part of our system. Now what we have is a rule which help us to formulate sentences, and we have a set of alphabets that makes a language for our system. Now we go on to the next part, which is axioms. We are saying that given any deductive system, we are able to identify fundamental truths of that system, and these fundamental truths are called axioms. What are the axioms of this system? Now there can be so many systems of deductive logic. That means deductive system for sentential logic. But the system that we are talking about is constructed by Russell, Bertrand Russell and A.N. Whitehead, and their system has been presented in their book Principia Mathematica. So there are other systems like Hilbert system, but we are not interested in their system for the time being. But our system is associated with the philosophers and logicians mentioned. So in their systems, we have identified 5 axioms. Axiom 1. P or P implies P. This axiom is called tautology. Axiom number 2. Q implies P or Q. This axiom has been named as addition. Axiom number 3. P or Q together implies Q or P, named as permutation. Axiom number 4. P or Q or R together implies Q or P or R. This is called association. The 5th axiom, Q implies R together implies P or Q implies P or R, and this axiom has been named as summation. How do we make sense of these axioms? Maybe let me help a little bit. What are these truths about? Let us look at axiom number 1. P or P implies P. That means given a conditional sentence involving just one variable, if the antecedent is a disjunction of itself, that is here P, then we have P in the consequence. Whatever be the truth value of P, the sentence is always true. Axiom number 2. Given a conditional sentence involving 2 variables P, Q, such that if Q is the antecedent and P or Q comes as the consequent, then no matter what truth values you assign to Q or P, you will always have true for your sentence, the truth value of the sentence. That means here, if Q is true, you can disjoin. That means you can connect with any other sentence involving disjunction and the sentence is always true. Look at axiom number 3. What does it say? Given a conditional sentence involving 2 variables P and Q, such that in the antecedent, if we have P or Q, in the consequent we have Q or P, that means we have reversed the order of disjunction. The first disjunct in the antecedent comes as the second disjunct in the consequent. Even if we reverse the order of the disjunction, it doesn't change the truth value of the sentence. So no matter what truth value you assign to P or Q, if it is in this form, the sentence will be always true. We go to axiom number 4. In a conditional sentence involving 3 variables P, Q, R, such that in the antecedent we have these 3 variables P, Q, R, they are joined by a disjunction. That means disjunctive connective, and in the antecedent we have these 3 variables Q, P, R connected by again disjunctive connective. Now if that is the case, we see here that the sequence of the disjuncts have been reordered. But even if we change the order of the disjuncts, if we are using disjunction in this manner, the truth value of the sentence doesn't change. Suppose we have 3 countries, Germany, India and Pakistan. Now we say in the soccer match, we are saying either Germany win or Pakistan or India will win. And in the consequent, if we say either India or Pakistan or Germany wins, the truth value doesn't change. That's just to cite an example. Now we move on to axiom number 5. What does it say? In a conditional sentence involving 3 variables P, Q, R, such that 2 variables occur in the antecedent of that conditional statement Q, R, and this Q, R are connected by implication. Q implies R. Then in the consequent, we have like this, P or Q together implies P or R. When we have such a situation, then no matter what truth value we assign to each of the variables here, the sentence is going to be true. So together, these are what we call axiom for our system. Now we move on to the next part, which is transformation rules. Rules for deriving theorems from axioms. The first rule is called modus ponens, or rule of detachment. That is, given a sentence alpha implies beta and another sentence alpha, and if these two sentences are true, then we can infer the truth of the sentence beta. Alternatively, we can also say that if alpha implies beta and alpha is provided, then we can infer beta. Let us try to explain this rule with the help of one example. Let us try to explain this rule with the help of an example. Suppose we are given these formulas, not Q or P or Q together implies P or not Q or not Q, and not Q or P or Q. This looks like alpha implies beta and alpha. Look at the structure of this argument. Given this, we can infer the conclusion P or not Q or Q. So we are done with the first rule, which is rule of detachment or modus ponens. Now we look at the second rule of transformation. It is called rule of uniform substitution. If a sentence beta is replaced uniformly in all occurrences of a propositional variable delta occurring in a thesis A, then the resulting sentence gamma after the replacement is also a thesis. Now let me put it this way. Suppose we have a sentence or what is so-called thesis. Now thesis can stand for both axioms and theorems. In our derivation, axioms and theorems are generally known as theses. In other words, whatever is derived is true. So if we have a thesis, that means if we have a true formula, what we can do here is, given a formula alpha, now you can change sub-formulas in the formula. So if there are sub-formula like delta, you can replace it with beta. So every occurrence of delta can be replaced by beta. So if that is being replaced, what sentence we get is actually a new sentence, gamma. I repeat, given a sentence alpha and a sub formula delta, every occurrence of delta can be replaced by beta. When these are replaced, we get a new formula gamma. So even if we replace like this, we will still have thesis. In other words, replacement will not change the truth value of the sentence. Now let me give an example for this rule of replacement. Let us consider this formula. Q implies P or Q. Now every occurrence of Q can be replaced by negation Q. So if we carefully look at this formula, this will still be true. What we are saying here is, in a formula, if any part of the formula is uniformly replaced by another formula, the truth value will still remain the same. Given this language appropriate for sentential logic and the axioms and also rules, now we can transform, or rather we can derive theorems from these axioms. So we will look at the derivation. What is a derivation? We will say that a derivation in our system is such that it will be arranged in vertical order, top to bottom, such that each step is either an axiom or derived by the application of one or two of the rules, or a theorem, or replaced by logically equivalent expression. In our derivation, we will have this as our formulas. One, it will be axiom. If not, it will be a theorem, which means it has been derived from the axioms, or by the application of one or two of the rules mentioned above, we are able to generate a new sentence, or a sentence is being replaced by a logically equivalent formula. So if our sentences in our derivation are one of these four types of sentences, then they will be considered as valid derivation, or they will be called theses. In other words, these are all true sentences. So given these axioms, let us try to derive some theorems. Let us try first theorem. We begin with example. Let us try to derive some theorem from the axioms. Let us try theorem number 1, which says syntactically entail P implies not P together implies not P. Given our axioms and our transformation rules, how do we derive this theorem? Now we can look at this one. We have, for this we need axiom 1, because here we are only using, rather there is occurrence of only one variable P, which is giving us a clue that we will need axiom number 1 to derive this theorem. So we introduce axiom number 1, P or not P together implies P. Now we can apply the rule of uniform substitution. Now if we uniformly replace every occurrence of P by not P, we can get a new sentence. Not P or not P together implies not P. Now by the rule of logically equivalent expression, this disjunction can be replaced by implication. So what we have now is, in our step number 3, P implies not P together implies not P, which is the theorem. Let us try to derive another theorem. We will now name it theorem number 2. Here it says Q implies P implies Q. Now we are using two variables here, and somehow it looks like axiom number 2. So intuitively we will appeal to axiom number 2 and use this axiom to derive this theorem. So we state axiom number 2. Let us try to prove yet another theorem. We will name it as theorem number 3. Can we show that P implies not Q together implies Q implies not P to be true? In other words, can we show that this is a thesis? In other words, can we derive this sentence by correct application of transformation rules from axiom? Given the structure of this formula, it looks like axiom number 3. So we will appeal to axiom number 3. So we state axiom number 3 as our first step. P or Q together implies Q or P. Now we can uniformly substitute each occurrence of P by not P and each occurrence of Q by not Q. What happens when we do that uniform substitution? We get this formula. Not P or not Q together implies not Q or not P. What we do next is introduce logically equivalent expressions. So we will change every occurrence of disjunction, rather every employment of disjunctive connective can be replaced by its logically equivalent conditional connective. If we do that, we have this one: P implies not Q together implies Q implies not P, which is actually the theorem that we want to derive. We will go on with this derivation. We will try to derive another theorem. We will call it theorem 4. What is that? P implies Q implies R together implies Q implies P implies R. So here we are employing 3 variables, and it looks like we can appeal to axiom number 4 to derive these theorems. Obviously, axiom number 1, 2, 3 will not work here because they are limited to just 1 or 2 variables. So by default, we will have to appeal to axiom number 4. We will state axiom number 4 as our first step. P or Q or R, the whole thing implies Q or P or R. Now we can apply the rule of uniform substitution. If we replaced every occurrence of Q by not Q and P by not P, just like we did in our theorem number 3, what we have is this: not P or not Q or R, the whole thing implies not Q or not P or R. Now if we replace this use of disjunctive connective by its logically equivalent truth functional connective implication, then we will get our desired formula, which is theorem. P implies Q implies R together implies Q implies P implies R. To get familiarity, we will still try another derivation of theorem, which we will call it theorem 5. What is theorem 5? Q implies R together they imply P implies Q implies P implies R. So can we derive this formula from axioms by correct application of those rules? We will try. By looking at the structure of this formula, it appears as though we can apply axiom number 5. So we will first state axiom number 5, which is Q implies R together implies either P or Q implies P or R. Now we need to uniformly substitute variables such that we get our desired result. How do we do that? We will replace each occurrence of P by negation P. So if we do that, what do we have? Q implies R together implies not P or Q implies not P or R. Now, having uniformly substituted P by not P, if we can apply the rule of logical equivalence, we get this one. So this junction is going to be replaced by implication. Q implies R together implies P implies Q implies P implies R. So that's how we got our theorem number 5. All these derivations we have done so far look somewhat easy. Let us try a more complicated derivation, which is theorem number 6. And theorem number 6 look like this. P implies Q together implies Q implies R together implies P implies R. Now, how do we apply correct rules so as to derive this theorem? It involves 3 variables, but we need to do more than we need to reason more to derive this, because the axiom number 4 and 5 both deals with 3 variables. So how do we do that? Let us try with something which is already proved. Now, what do we mean by that? We said in a derivation that we can have axiom or theorems. So what is happening here is theorem number 4 has already been proved and now it has become part of our derivation. So in which case the theorem number 4 we have already derived can be employed to use to derive this formula. So we go to theorem number 4 and we state it here. P implies Q implies R, the whole thing implies Q implies P implies R. This is theorem number 4. Now we need to reason more. We have to look for suitable substitution of formulas. That means we need to replace some formula by another formula such that by application of suitable rule we will get our desired formula. Now just uniform substitution is not going to work here. So we will have to introduce rule of detachment, or what is so called modus ponens. Before that we will try substitution. Every occurrence of P will be uniformly substituted or replaced by Q implies R, and every occurrence of Q will be uniformly substituted by P implies Q. Every occurrence of R likewise will be replaced uniformly by Q implies R. So what happens if we do this uniform substitution? We will get a formula something like this. Q implies R together implies P implies Q implies P implies R. The whole thing implies P implies Q implies Q implies R implies P implies R. This is a difficult reading, but having got this formula, now we can think of applying another theorem which will be required to derive the next step. So if we introduce theorem number 5, probably we can apply detachment rule. So what is theorem number 5? Theorem number 5 says Q implies R together implies P implies Q implies P implies R. Now if we introduce this, it looks like the antecedent of the conditional statement we have in the step number 2. So it looks like alpha implies beta and alpha 2 and 3, which means we can apply the rule of detachment to derive the consequence of the step number 2. So if we apply that rule of modus ponens, we have step number 4. P implies Q together implies Q implies R implies P implies R. That is, by applying the rule of detachment on step number 2 and step number 3, we have derived step number 4, which is what we want to derive. That is theorem number 6. P implies Q implies Q implies R implies P implies R. We have just seen that given axioms and rules of transformation, which is uniform substitution or detachment, we can derive theorems from those axioms. And each theorems, when proved, can be employed to derive another theorem, which we have seen in while proving theorem number 5. or rather theorem number 6. We can derive more theorems actually. So without involving a process of derivation, I'll just now highlight what are some of the important theorems which can be derived given those axioms, derived theorems and rules of transformation. Theorem number 7, P implies P. This can be also derived from the axioms. We can also derive P implies P, which can be mentioned as theorem number 8. Given those axioms, we can also derive another theorem, either not P or P. We can have more theorems. Let us say theorem number 10, P or not P, which is just the reverse of what we have in theorem number 9. We can have more theorems like P implies not P, which can be taken as theorem number 11. We can have more theorems like in number theorem 13 we have not P implies P. Theorem number 14, not P implies Q together implies not Q implies P, or theorem number 15 like P implies Q together implies not Q implies not P. With that, we will try to summarize what we have learned today. What we did was introduce the language appropriate for this system, and then we also introduced some axioms, and we went on to introduce and explain rules, which are of two types: rule of detachment or rule of uniform substitution. In addition to that, we have also mentioned that given a formula using some connective, it can be replaced by another logically equivalent expression. So that is how we introduce disjunction in our system. Having introduced these rules and along with the axioms, we have tried to derive some theorems. So we have derived theorems 1 to 5 or 6, and then we have also highlighted some important theorems. In all these, what we are trying to do is this, that given any deductive system, it is possible to develop a kind of axiomatic procedure which will help us to identify axioms or so-called fundamental truths. And given those fundamental truths, we will be able to understand how truths, or rather all the truths in that domain, are interrelated. So this is axiomatic system for sentential logic. Before I finally stop my lecture, let me add one more. If you have doubt and you want more information, refer to e-text. There you will have references and required web links. Thank you.